Welcome back to everyone. This is Physics with Mr. McQueary. Today's lesson is going to focus on unit conversions. Our learning target for the day is to convert one measurement from one unit to another. So this might be from imperial units to the metric system, or maybe from the metric system to imperial units. We're going to build up in complexity with each example. And we're going to talk about maybe why this is important, why you would need to know this skill. Okay, consider this gallon of milk. You've probably seen this a lot of times at your local Walmart, and maybe you haven't thought twice about looking at the label. Well, below's nutrition facts list things like keep refrigerated and the barcode and how much is included. All right, gallons in the English or the imperial system. And liters, of course, we know are from the metric system, right? And you may have bought so many gallons of milk and used them so often that you can visualize what a gallon looks like. It's probably not real important to you that it happens to be 3.78 liters, right? But consider a situation where maybe you do need to know the difference between the metric system and the imperial system, like driving down the interstate, all right? If you hit the accelerator on your car and go 105 miles per hour, you are going to be pulled over because you're going much faster than 105 kilometers per hour. In the English system, or the imperial system, that's only equivalent to 65 miles per hour. So if you are driving overseas, let's say in Europe or any other country besides the United States, Myanmar, or Liberia, you're going to need to know the metric system if you are driving. Let's do an example problem, all right? Example problems are a great way in physics to get used to the idea of pulling out information that is important to you, devising a plan so you can use that information, and pay attention to details. All right, so if you've seen the movie Happy Gilmore, you know that he has an unorthodox swing, to say the least. And you also know that Bob Barker has a cameo in the movie. All right, now instead of getting into a fight, we're going to say they have a conversation on the metric system instead. And Bob doesn't know how many meters Happy just drove the ball. So let's pick out the important parts of this. All right, number one, 445 yards seems to be important. Number two, it appears that meters is also important because we were asked to find that eventually down the road. And there's also a nice conversion factor we're giving you. Look, that 1 meter is equal to 3.28 feet. That's probably going to be useful. And we also have one small detail. We want to round to the nearest meter. So when we do get our final answer, let's keep that in mind. Our given information, we have 445 yards and our conversion factor. We are asked to find the length in meters, and we have listed out our steps here because you can't necessarily go from yards straight to meters unless you're given a conversion factor. Our conversion factor is not that. It goes from feet to meters. So in order to get there, we have to go from yards to feet to meters. Those are the steps we're going to take. Let's remember our given information up here. That can be useful. And we're going to start by drawing some train tracks. All right. And on those train tracks, the first thing we're going to do is we're going to write our given information. That's the first thing you're going to write down. All right. The next step we're going to do is we're going to try to get rid of those yards. All right. We want to go from yards to feet. So we want our final answer to be terms of feet. All right. How do we do that? Well, think back to math class. All right. If I have something like this, all right, I have yards here, and feet in the numerator. Let's change those to y, and f, right? If you were to multiply these across, all right, if you're trying to simplify this kind of like you would your mathematical ratios, if we had, instead of brackets and train tracks, if you had parentheses, then these yards would divide out because a yard divided by yard, or y divided by y in algebra, is just 1. And we'd be left with feet. So when you're doing these conversion factors and you want to get rid of something, as we like to say, we're going to make sure that they're opposites. We need to make sure that one of those are in this case, yards, one of these units is in the numerator, and we need to make sure no one is in the denominator. All right. And now we're going to fill in our conversion factor. So last time I checked, 1 yard is roughly equal to 3 feet. All right, that's our conversion factor there. So if we're going to go ahead and simplify this, you know that our yards would cancel out, we'd be left with feet. But our answer is not asking for feet, it's asking for meters. So we need to convert from feet to meters. So we're going to draw another train track. All right, and remember we said that if we have our units in opposite areas, namely if we have 1 in the numerator and 1 in the denominator, then they are going to cancel out. So we'll write our feet, and we'll write our desired unit in the numerator. And this is where our conversion factor comes in. We know that based on our given information that 3.28 feet is equal to 1 meter. So we're going to go ahead and fill that in. Okay, so we filled out our train track method. Now we're going to finish by double checking our work. All right, so last I checked, we have yards over here, yards down here. Those will cancel out. Excellent. Feet and feet should cancel each other out, and we're left with meters. That's what we want to be left with. One of the common mistakes I can see is if students maybe flip this and get yards up here and feet down here on the bottom, you would multiply across and get yards squared, and feet would still be down here in your denominator. And you don't want that. You're trying to solve for meters, not yards squared per foot. All right. So the next thing we're going to do here is we're going to take this information, these numbers, we're going to multiply them. All right, right across the top. So 445 times 3 times 1. You'll display that as 1,335 meters. And then we're going to multiply everything across the bottom. So 1 times 3.28. All right, you've noticed that we've gone ahead and brought our unit down. These meters made their way down here, and that's good because it's easy to forget after a little bit of math to include your units, and those are very important. All right, we'll simplify this, and you see that we are left with 407 meters. Now, if you do this at home when you're working along, you'll notice that it's not exactly equal to 407 meters, but remember our original problem asked us to round to the nearest meter. All right, that's example problem number 1. We're going to go ahead and step up to example problem number 2. All right, number 2 over here, Jean Calment is the oldest verified person to have ever lived, according to Guinness Book of World Records. She lived 122 years. This is a picture of Jean, and she is roughly 20 years old in this picture, so about the age of most of you that are working these problems. And she was still alive until 1997, so she saw quite a bit during her lifetime. For those of you that are mathematically inclined, with a little summation help, if you use a new candle to represent every birthday, so 1 candle for 1-year-old, 2 candles for 2-year-old, 3 for 3-year-old, she would have over 7,000 candles. So we want to figure out how many seconds Jean lived. So the important things to look for here is our given, 122 years. It's easy to get distracted by numbers like this. They're not important, right? We don't need to know that. And we need to convert to seconds. Now, we're not given the nice handy conversion factor last time, and we're also not given any directions on when to round. So we can have a little more leeway with that. All right, so our given information is 122 years. We want to find seconds, and you can see all the steps we're going to take. Instead of just having 1 or 2 steps, this will be more steps than that. All right, we got to go from years to days to hours to minutes to seconds because you probably don't have a conversion factor that takes you straight from years to seconds. So first thing we're going to do is draw our train tracks. The second part is to write down our given information. All right, that always goes in the top left corner. All right, remember, we want those years to cancel out, and right now they're in the numerator. So we need to include our next one in the denominator, so those will divide out. We want to convert years to days, so days will take the place in our numerator, and our conversion is 365 days for every 1 year. So far, so good. The next step is to go from days to hours. So our days are going to occupy our bottom spots. They will cancel out, and hours will take the top. Last time I checked, there's 24 hours in a day. And so we will include our conversion factor. We're going to go from hours to minutes. So we'll do the same thing here. Hours will be at the bottom, minutes in the top. And there is a 60-minute to 1 hour ratio. The last thing we're going to do is go from minutes to seconds. So we have minutes in our denominator, seconds in our numerator, and we have a 61 ratio once more. Excellent. All right, so everything looks set up. Let's check our units to make sure they're in the correct place. So we have 2 different years. Those will cancel out. We have the days that will cancel out, hours that will cancel out, and minutes that will cancel out. So we are left with seconds, which is what we wanted to be left with, correct? So good job so far. Everything from here is just math. Okay, we're going to go ahead and multiply everything across the top and get a very large number indeed. And across the bottom, if we multiply these, is just 1 to the 4th power, which is 1. You've noticed I've kept my unit. Very important again. And this is an excellent opportunity to review some of our rules for scientific notation. Remember, for scientific notation, we need exactly 1 number to the left of our decimal. All right, in this case, we're going to move this decimal all the way over to between 3 and 8. All right, now the only question is, what will our exponent be? Well, we move that 1, 2, 3, 4, 5, 6, 7, 8, 9 different times to get to that spot. And the only question now is whether to keep that positive or change it to negative. Well, our original number is very large, so we're going to keep that as a positive 9. So our final answer is 3 8500ths times 10 to the 9th seconds. So far, so good. Remember, we didn't have any rounding guidance, so we can leave it like this. The final example problem we're going to do together is the trickiest. All right, our current land speed record is 763 miles per hour, and we want to know how fast that is in meters per second. We are going to be rounding to the nearest tenth, so now we have some guidance for our rounding, and we're given a nice handy conversion factor. All right, so let's go ahead and just write that out. Without our distractors, we have our given, we want to find, and we're given our steps. Now, you'll notice that there are 2 different areas when it comes to steps, because we have to convert both the miles to meters and the hours to seconds. All right, this may seem difficult at first, but we're going to show you how to use our train track method to simplify this. Same as always, we're going to draw our train tracks and then list our givens. So in this case, we have 763 miles traveled per hour. So our 763 miles will occupy the numerator, and our denominator will house our hours. So we have 763 miles per 1 hour. That's our ratio. Okay. Now you have a choice at this point. You can either convert miles to meters first, or you can convert hours to seconds. Personally, I like doing miles to meters first because it's my first unit. All right, so if we want to get rid of miles and be left with meters, where should we put our miles? In the denominator, right? Those should cancel out. Our meters, what we're left with, will be in our numerator. The conversion factor we were given in the example problem is 1,609 meters for every 1 mile. Excellent. So we are finished now with that conversion. Now for time. We need our hours to cancel out, so our hours will be up here in the numerator. All right. And then we convert to minutes, so our minutes will be in the denominator. It is okay that these hours are separated by a term here in the middle. They can still cancel out. All right, let's go ahead and write our conversion factor, 60 minutes for every 1 hour. So now we have our answer in terms of meters per minute. So we're not quite finished. We need to convert from minutes to seconds. All right. If we want our minutes to cancel out, we need to put them in the numerator and our seconds in the denominator. And we're also going to have that 60-to-1 ratio to fill in. Let's double check our units. Our miles will cancel out. Our meters are left over. Excellent. So our hours will be the next thing to cancel out. Our minutes will cancel out. So we're left with meters per second, which is what we wanted to be ended up with anyway. So far so good. Now the math. Multiply everything across the top. We're left with over 1 million meters. And then we're going to multiply everything across the bottom. So 3,600 seconds. You'll notice that this time, both the meters and the seconds are left over. So we need to include them in our answer down here. If you type this into your calculator, you get 341 meters per second. Now, why is that 0 there? Well, the original question asked us to display our answer to the nearest tenth of a meter per second. All right. So we've done 3 example problems. We've built up the complexity each time, but with this railroad method, you can see we can handle just about whatever anyone can throw at us. Our learning target today was to convert a measurement from one unit to the other. Till next time, see ya.